Yeah, hi there. My name is Tobias, and I'm an MRC fellow here at the Cognition and Brain Sciences unit. And I will today talk to you about restoring the sense of sound, about cochlear implants, how they work, what they are, and our research to improve them. So, when you hear sound, for example, me talking now, or any other speech, then it will always kind of travel through your ear, through the ear canal to the tympanic membrane, and then reach the cochlea, the inner ear, where it is translated into auditory nerve signals that lead up to your brain and then result in perception of speech or sounds or music or whatever there is. And the crucial bit really here is happening in the cochlea, which is a snail-shaped bony structure, which houses the basilar membrane and, most importantly, the hair cells that transduce acoustic waves or vibrations into neural signals that lead up to the brain then. And here on the right, you can see the inside of this snail-shaped structure, with in green shown these hair cells, the transducers, and in red shown the auditory nerve fibers that are connected to the hair cells here. And in normal hearing, when you don't have hearing loss, then here is a microscopic picture shown how this looks like. So you have a row of inner hair cells, which basically receive the sound information and detect it. And the outer hair cells are fulfilling a function to amplify the sound very quickly, so to make it easier to hear sound. But in a case with hearing loss, there's damage in the cochlea, as you can see here. So hair cells may be completely gone, they may be damaged, they may be degenerated, overall not leading to the intended transduction of acoustic signals into electric nerve signals. And there's many reasons for hearing loss to happen. This could be age-related, simply by getting older, noise-induced, because at work or in concerts or in music clubs, you listen to too much noise or loud music over your lifetime. There's sudden loss, there's genetics involved sometimes, there's ototoxic drugs. So there are many different reasons that can lead to this loss in hair cell or transduction, which is called sensory neural hearing loss. And it's quite prevalent. So worldwide, we have nearly half a billion people affected by hearing loss. And there's more than 1 billion people at risk due to the noise exposure that I mentioned in the future. In the UK, there's 11 million or even more now, 1 in 6 affected by hearing loss. And hearing loss is typically measured or assessed using the audiogram, which is by playing some little tones to the listener and then measuring the threshold at which point you can hear these tones. And if these thresholds are below or up to 20 dB hearing level, then you consider this a normal hearing threshold. And with every step of amplification that you have to apply, so how much louder you have to make the sound so that the person can still detect it, you classify these steps then into mild, moderate, severe, profound hearing loss, etc. And for the mild to moderate cases, typically you can use acoustic hearing aids that just simply amplify. And they do a bit more than just amplifying, but the main function is to amplify the acoustic wave so that you can hear it better again. But for severe to profound hearing loss, hearing aids, acoustic hearing aids, do not usually work that well. But this is still a very important group, because there's about 1% of the adult population globally affected by this severe to profound hearing loss, and 1 in every 1,000 children younger than 3 years may have this. But what you can do here is supply cochlear implants, and this would work for many of those that have severe to profound hearing loss. So what is a cochlear implant? It's a surgically implanted neuroprosthetic device that provides a sense of sound via electrical stimulation to the auditory nerve. They can be used by older people that may have lost their hearing due to their age. They can be used by children, kids, or even infants that can be provided with a CI under the age of 1 even. There's now more than 800,000 people worldwide that have a CI or use a CI. And in the UK, more than 2,000 new CIs are received every year. It's really a big success story because many or most people that use CIs achieve really good speech perception without lip reading. And some may even go as far as and really enjoy music again. So how does it work? The cochlear implant consists of two parts. We have an outer part, the speech processor, which looks a bit like a hearing aid. It's worn behind the ear or on the head. And we have the internal part, the implant. And these two hold together via a magnetic link, and they have a transmitter coil here and a receiver coil, and they hold here, they talk to each other via magnetic fields. The internal part also has a small electrode array that is surgically implanted into the cochlea. So it's kind of pushed inside this snail-shaped structure here, and then you can see here these little contacts. These are electrical contacts that are used to stimulate the auditory nerve here in the center of the cochlea then. And this electrical stimulation is schematically shown here. So every red blink shows you an electric pulse that is delivered and then received by the auditory nerve fibers here, which then leads up to the brain. So in order to do so, the cochlear implant records the input sound. These are the acoustic waves in the environment of the listener via microphones. It then does some signal processing to the signal. It, for example, splits the signal into different frequency bands using a filter bank approach. And that is important because then in each of these different frequency bands, information is extracted from the sound, and that is used to modulate electric pulses. So these little pulses here, which have a high part and the low part, are then shaped by the frequency information in that specific frequency band, and then delivered to these little electrode contacts that I mentioned earlier, whereas where you have at the beginning of the array here at the so-called base of the cochlear, you have the high tones delivered, the highest frequencies that you can hear, for example, a high beep tone, and at the tip, at the apical, so-called apical part of the cochlea, you have the low frequencies. So it goes from low up to high frequencies. And there are quite a few challenges now that apply to cochlear implants, because as good as this may sound in theory, in practice, as usual, there is some limitations here. So when you imagine now having this cochlear electrode array inserted into the cochlear, and you stimulate at one contact here, for example, then the current would be ideally just exciting the neurons that are closest to that contact. So that when you then activate a different contact in order to stimulate, for example, a speech signal or a speech signal in background noise or a music signal, that you could differentiate these different frequency bands from each other. But unfortunately, electrical current flows in every direction, and you have a lot of spread or overlap between these different channels, and that effectively reduces the spectral resolution that cochlear implants can deliver. And this is one main limitation here of the electrode nerve interface of cochlear implants, is the spread of electrical current. And another one is the status of the auditory nerve. You can imagine if someone had a long-term hearing loss, then the auditory nerve has not been used or excited much, and that may have led to a degeneration or a partial degeneration. So in some regions along the cochlea, the auditory nerve may not function as well anymore. And these are two main reasons that lead to difficulties for people that use cochlear implants in perceiving complex sounds. This could be speech in a noisy environment. For example, when you're in a restaurant or in a classroom and there's a lot of background sounds going on, then it's really difficult for a person with a cochlear implant to make sense of the speech that they want to listen to, because all the interfering sounds kind of make it very hard to hear it. Same happens in music, which is a very complex signal. And the reduced spectral resolution of cochlear implants really makes it hard to enjoy music or to hear it well. And also spatial signals, so trying to localize where sound is coming from, which may be important as well if you're in a noisy environment. It's much more difficult with cochlear implants. So I want to give you an example here for the speech and noise case that I described. Firstly, I play you a simulation of how it would sound if you had a CI. This is not perfect. This is just an example, but nevertheless, please and listen. I will make it a bit louder. Without the background noise now. And the acoustic signal for this would be...
They moved the furniture. They moved the furniture.
So you could probably easily understand this acoustic signal and background noise.
They moved the furniture.
And if I play now again the simulated signal, it may be much easier to hear this as well, but at first it was probably very difficult for you. So you can see there's much less information in terms of the spectral resolution in the signal, and that makes it really quite hard to understand speech, especially in background noise. So we perform several different research themes to improve cochlear implants or to understand them better. For example, we work a lot on characterizing the electrode nerve interface, trying to understand better how we can measure the status of the auditory nerve, for example, or how we can assess or detect how much current spread there is in the cochlea for a given patient, for example. Another line of research is to measure pitch and temporal modulations with cochlear implants, which are important as well when you listen to speech or music. Then we work on localization of sounds, trying to improve how people can hear where sound is coming from, and on, in general, speech perception, trying to improve speech and noise perception, for example. And I would like to give you one example here. So in order to showcase that, you could have this signal here, which is speech in background noise. And the goal here simply is to make it easier to perceive, to see it in this case, or to hear it again. And how we do that is we take lots of examples of speech and background noise. This would be data collected, different speech recordings with different background noise recordings simply mixed together to simulate many, many different cases of speech and noise. These are then fed to a machine learning algorithm, which is a clever algorithm that learns based on examples. And it kind of iteratively learns to segregate the speech signal from any kind of background noise. And then you could use this algorithm once it's trained, once you have optimized it, and put it into a cochlear implant as a front-end processing. So it would get rid of the noise before it is played to the listener. And because cochlear implant listeners really are performing really well with speech and quiet, if you reduce the background noise, then maybe they could hear the speech better out, even in noisy situations, with the help of such an algorithm. And so we assess and evaluate this. We invite cochlear implant listeners to our institute, play them different sounds, for example, speech and noise, and also these recovered speech signals where we evaluate or test these algorithms. And then we see, do they understand speech better in the case with the algorithm, and how much better, and would that depend on different background noise situations, etc. And then we evaluate these results. So these were some limitations of CIs, but there's a lot of achievement been done over the years. So, for example, there has evidence for large benefits in quality of life in terms of communication, entertainment, and in terms of safety. It's a very safe device. There's very low risks associated with it due to the surgery or device failure. One issue is maybe that the outcomes are pretty variable, so it still remains a challenge to predict which person will do well with a cochlear implant and which person won't do well. And that's a bit of a tricky thing, as you can imagine, if you can't really promise the outcomes to the patient beforehand. Children can receive CIs even under the age of 1 year, and the earlier the better here to implant the CI, because that would improve the language development, emotional development, etc. Adults can receive a CI at any age, really, as long as the auditory nerve is intact and functions, because the neurosensory development and the brain basically makes sure to relearn that new type of sound, that electrically stimulated sound of the cochlear implant, quite successfully. There's a bit of practice involved, and people have to dedicate some listening effort, but most people can really learn to use that signal. So to summarize, hearing loss affects a lot of people already and will affect many more people in the future, unfortunately. Cochlear implants are one solution that translate the acoustic signal into neural signals via electrical stimulation of the auditory system. They achieve good outcomes for speech, especially in quiet, but there are many or several limitations. As I said, speech and background noise, music signals, localizing sounds, for example. Cochlear implants can be given to infants or to the elderly, to anyone really who has a working auditory nerve. They have been a big success story, but there remains room for improvements, and that is why we do more research. We try to make them better, to close the gap, basically to make them more similar to normal hearing and to restore the sense of sound with cochlear implants, really. So I would like to thank you for watching me talk here. I would like to acknowledge the Cambridge Hearing Group, which, if you are more interested, you can find more information on our website here on hearing research that is going on in Cambridge. I would like to acknowledge my funding source, which is the UKRI MRC fellowship called Restoring the Sense of Sound. And I would like to credit also my colleagues and other hearing researchers here at the CBU, which is a great team. And I would like to thank you again for the attention.